We're kind of blending two things together. We've talked about those safe dosages, and we did some examples on those last time. And we had examples with dosages based on weight. So things like we might have a doctor's order for 4 milliliters to be given every 6 hours, Q6H. For a patient, that is 33 pounds. We look at the label on the bottom. The label for that medication says 1.5 to 2 milligrams per kilogram per day. So, and also on the label, it gives us the concentration of 50 milligrams in 25 milliliters. So relatively low concentration. Our first step is we have to convert our patient's weight from pounds into kilograms. We'll do that divided by 2.2, which gives us 15 kilograms for that patient. So then our next step is going to be to convert or to take that weight and use it to find the dosage based on the weight. So we have 15 kilograms over 1, and we're going to use the max dosage. It seems that's the pattern we've been following into. So kilograms on bottom, so they go away, is 2 milligrams per kilogram. So that's per 1 kilogram. The kilograms will cancel out. And now, so that matches up with the doctor's dosage of milliliters, we need to convert that to milliliters. So milligrams go on bottom, so they cancel out. 50 milligrams and 25 milliliters. The milligrams cancel out. And now what we have is milliliters. This is our only unit here, which is what we want. So we'll go ahead and multiply this all out. 15 times 2 is 30, times 25 is 750 milliliters. Over 1 times 1 times 50 is just 50. That ends up being 15 milliliters. Now we have to go back and look at our time constraint. That is per day, so that's 15 milliliters per day. The doctor's orders are 4 milliliters every 6 hours, which looks close, but there's going to be some issues that come up with it. Let's take a peek. So we've got that 15 milliliters. That's per day, so that's per 24 hours. We want to titrate that to 6 hours. So the hours aren't a factor, so it's just 6 over 24. So 15 times 6 divided by 24 is going to give us 3.75, I believe. And it is 3.75 milliliters. That's every 6 hours. So the doctor's dosage of 4 milliliters every 6 hours is a little on the high side. We don't need to find the minimum here because we are already over the maximum, so we're outside of the range. Otherwise, we could do a titration to find the minimum dose. Any questions on finding those types of safe dosages? Okay, so one that we didn't get to is on an IV. So let's say the doctor has an order for 20 drops per minute for a patient that is 66 pounds. And we read the label, and our label says that we are to give 8 to 10 milligrams per kilogram per hour. And it gives us 25 milligrams in 8 milliliters. And it also gives us a drop factor of 12 drops per milliliter. So, as always, we're going to start off with our patient's weight. We've got 66 pounds. We turn that into kilograms by dividing by 2.2. giving us a 30 kilogram patient. We start off our calculation with the 30 kilograms. Put it over 1, and we have milligrams per kilogram here. I am going to use the maximum again, the 10 milligrams. Kilograms on bottom, 10 milligrams go on top. Per kilogram means per 1 kilogram. So the kilograms cancel out. Next step then, milligrams to milliliters. Milligrams go on bottom, so they cancel out. 25 milligrams in 8 milliliters. So the milligrams cancel out. We're now in milliliters. Well, this rate is given in drops per minute. Let's go ahead and convert this to drops right now. 12 drops per milliliter. So 1 milliliter on bottom, 12 drops on top. Milliliters cancel out. And let's go ahead and multiply this out. On top, we've got 30 times 10 is 300, times 8 is 2,400, times 12, I believe it's 28,800. I'm going to double check that calculation. It is 28,800. On bottom, 1 times 25 times 1 is just 25. So we divide that by 25. That's 1,152 drops. Notice that that is per hour is our time factor here. Doctor's orders was drops per minute. So we're going to have to make a conversion of the time. So this is drops per 1 hour. Hour on top, since it's on bottom to make it cancel, into 60 minutes. So that's 1,152 drops over 60 minutes, and we'll divide out the 60, giving us 19.2 drops per minute. So the doctor's order of 20 drops per minute is slightly high. Now, so we can practice the titration on the 8, let's go ahead and do what would the minimum be. We have that 19.2 drops per minute. And I'm going to titrate that. We use the 10 was the maximum. Let's change it to 8 for the minimum. So what we used goes on bottom. What we're changing it to goes on top. 19.2 times 8 divided by 10 gives us 15.36. That would also be drops per minute. So the safe range for this medication would be from 15.36 to 19.2 drops per minute. That 20 is slightly out of that range, so that would be something to confirm to make sure the doctor's aware that it's slightly outside of the recommended range. Okay, so we've had those types of dosages. Our next step, we mentioned briefly last class, dosages based on body surface area. From here on out to be abbreviated BSA. Body surface area, those calculations are usually based on, or for patients who have burn victims or skin conditions like eczema and things like that, where it's either going to be a topical medication or it is given internal, but it is to treat a skin condition of some sort. So the first thing we have to be able to do is find body surface area. So if our patient has things that are measured in standard units, which is where we're going to start, our height is going to be measured in inches for standard units. So if we were given, someone who is 5'9" tall, we have to convert that into inches. And our weight is going to be given in pounds. Our formula for a body surface area in meters squared. So we're always going to find the body surface area in meters squared because our medications are going to be given as per meter squared. With those standard units, body surface area in meters squared is the square root of the height times the weight divided by 3,131. So let's take a peek here. If we have a patient that has a height 5 foot 8 inches and a weight of 142 pounds. That body surface area is going to be found by plugging into this formula. 5 foot 8. Well, we have to do 5 times 12 is 60. So 5 feet is 60 inches, plus the other 8 inches is 68 total inches. So a total height of 68 inches. So into our formula, it's 68 times 142 divided by 3,131. Now this can be punched, most of your calculators, you can punch this in all at once. Second square root. Now my calculator is going to put it under the square root sign. If you have a graphing calculator, yours should do the same. Unless you have a TI-83, it'll give you an open parentheses. Most of your calculators, your non-graphing calculators, will give you an open parentheses after the square root, and we'll just have to make sure we close our parentheses at the end. So 68 times 142 divided by 3,131. Notice you can put that in all as one line like that. We don't need parentheses in there. Now again, many of you, if you don't have the big bar of the square root going over all the numbers, you'd have to close the parentheses there. It equals, and we get 1.756 square meters. Usually we're going to round to the nearest hundredth. So 1.75 square meters is the body surface area for that patient. Well, we may have to calculate that body surface area in metric units. If we're using metric units, we need to have our height in centimeters and our weight. I'll label this as mass because this is technically a mass unit in kilograms. With those inputs, body surface area, again in meters squared, is the square root of, erase that, our height times our weight again. What changes is this constant on the bottom here. It's divided by 3,600 now. Remember the last formula that was 3,130. Those are constants based on the units being used. So let's say we have a patient that has a height of 140 centimeters and a weight or mass of 45 kilograms. Body surface area is going to be found by using the square root of 140 times 45 over 3,600. So again, we can punch this in the calculator all in one step. 140, square root of 140 times 45 divided by 3,600 gives us 1.322. 1.32 if we round to 2 decimal places, meters squared. We will always round body surface area to the hundredth of a square meter unless we are told otherwise in the problem. So this is the most precise way of calculating body surface area using a formula. There is a possibly quicker way if you don't have a calculator on you. It is something called a nomogram. A nomogram just means, the word nomogram just means it is a graphical way of doing a calculation. And it's done for many things. I've seen them used for converting temperatures, Fahrenheit, Celsius, among other things. Um, effective temperature for wind chills and effective temperatures for humidity and stuff like that as well. The nomogram for body surface area uses that height and weight, and it can be used for any units. And it looks like this. Now this nomogram, the example I have here, is actually two different charts combined together. For the actual body surface area nomogram, we're using the height here, the weight or mass over here, pounds or kilograms, and then the surface area, the body surface area, is given in this column here. What's in the box right here is actually a separate graph, separate table that's been put in there to take up space because these columns had to be spaced in a certain way to make them line up. Let me show you what I mean by that. Let's double check the examples that we've done here so far. Let's go back up to this first example. Oops. We had a patient here. Scrolled up too far. We had a patient here who was 5'8" or 68 inches and 142 pounds. Let's look at our nomogram for a height of 68 and a weight of 142. Well, our height is in inches here. 68, well, there's 65, 6, 7, 8. That's right there, 68 inches. A weight of 142. Now you can see here the weights are kind of jumbled. The lower weights are nice and spread out. But once we get over 100 pounds, they get to be pretty tight together. This is 140 right here. This is 150. So 142 is going to require us to kind of guesstimate in there. Somewhere in there, closer to the 140, obviously, than the 150. So now I'm going to construct a line there between the two. You could take a ruler if this were on paper instead of on the computer screen. You could do the ruler, you could take the edge of another piece of paper, whatever works for you. Often the edge of another piece of paper is what you have available to use. I'm going to format this a little bit here quick to make this easier to see. So let's make it red so it's easier to see and make it a lot thicker. Okay, so making that line thicker makes it a little less precise, but a little more usable here. So what we have here, let's change color, see if I can get rid of that. Oh, not going to do it for me today. So anyway, we see where this line lines up here. It goes from my height in inches, the 68, to my weight of 142. I apologize for the shadows. But where it crosses the body surface area column here, you can see it's right at or just below the 1.8. So this is 1.7, 1.8, and 1.75 is in the middle. So approximately 1.8 meters squared or slightly less. We go back here, we had calculated 1.75 meters squared. That is an exact number. So the nomogram may be going a little bit high, but within a few hundredths of a meter squared is close enough. Let's look at our example here with metric measurements, 140 centimeters and 45 kilograms. So let's look here at a weight of 140 centimeters. Well, let's just take my line here. We're going to drop this end down to 140 centimeters. You can see that's 140 centimeters, so I'm going to drop it on the axis at 140 right there. And got to check that weight again. It was 45 kilograms. So 45 kilograms is down here. Now this is 40. That's 2, 4, 6, 8, 50. So it's going to be between these two markings here, somewhere in there. Now you can see I'm not going to be perfect with where I get my endpoints, That's one of the other things that contribute to some of the error in this measurement. Now you can see this is between 1.3 and 1.4, almost dead in the middle. I'd say about 1.35. We're going back here, we calculated 1.32, so that's pretty close, again, within a few hundredths of a square meter. One of the weaknesses of the nomogram, there's a couple of weaknesses. One is it is not as precise. Yeah, you can see here we were a few square meters off from our formula value. And it requires, you have to have some space to set it down. You can't be just walking around, and line things up and make it work. You've got to have the ability to hold things steady and line them up, whether that's laying them down on a countertop or having a clipboard that you can hold steady enough to do it. The second big weakness of the nomogram is you must have it with you. You must have it. So if you don't have that with you at the time, you've either got to go grab one or some other method. So the strength of the nomogram, of course, is you don't have to do any calculations. With the readily available calculators now, the calculations are not so daunting. Of course, the formula has a strength of being exact. And, of course, you pretty much always have a calculator. If nothing else, you have one on your cell phone. Now, many hospitals and clinics right now are very strict on cell phone usage, by the way, for employees. So just because there's a calculator on your cell phone doesn't necessarily mean you'll have the cell phone with you. But most of them have gone to electronic charting. And those electronic charts do have a calculator built in. Well, let's do some more examples here of calculating body surface area. So let's take a patient who is 1.4, let's actually do 1.6 meters tall, has a weight or mass of 132 pounds. Let's find their body. Oops, 132 pounds. Let's actually adjust that. I don't want to, well, yeah, I don't want to mix that. 132 pounds, let's go with 60 kilograms. So I'm not mixing meters and kilograms together quite yet. So the body surface area in meters squared is, again, square root. 1.6 meters has to be converted into centimeters. From meters to centimeters is 2 spots on our metric chart. So we move the decimal 2 spots, 1.6 meters becomes 160 centimeters. So our body surface area is 160 times 60. Since these are metric, centimeters and kilograms, it's over 3,600. So we'll punch in second square root, 160 times 60 divided by 3,600. And we get 1.63 meters squared. Let's double check that one on the nomogram and see where the nomogram goes with us. Got 160 and 60. 160 here for the height. That's going to put us up right there, about. 60 kilograms is going to put us up somewhere in there. This lines up between 1.6 and 1.7, a little bit over halfway. So I'd say 1.5 or 1.65 something. 1.65, double checking. We had 1.63. So again, the nomogram is close, just a little bit off. You can see most of our examples so far, the nomogram has been giving us a number slightly high compared to the formula. Let's look at an example with standard measurement. So let's say we have a height of 6'1" and a weight of 230 pounds. So the first thing we have to do is convert our 6'1". 6 times 12 is 72, plus 1 is 73 inches. So our body surface area in meters squared will be the square root of our height of 73 times our weight of 230 divided by, now here's the thing, we got to remember which number goes on bottom. Since these are standard units, inches and pounds, is 3,131. So second square root of 73 times 230 divided by 3131. So 2.32 meters squared is the body surface area for that patient. Now, here's where we're going to find a third weakness of the nomogram. We have a height here of 73 inches. That's easy enough. That's right there. Our height actually goes up to 90 inches, which is 7'6". Don't see us needing to go higher than that. But on the other side here, the 230 pounds is not on the chart. We can see our chart goes up to 180 pounds. So the nomogram really only works for juvenile patients. Many adults are over the 180-pound mark. So the nomogram would not work for anybody over that weight. Let's go back and do another example here. This example, we're going to have a patient who has a height of 1.75 meters and a weight of 175 pounds. Now, looking at this, we can see first thing that comes up is our height is given in metric and the weight is in standard. So there's two things we have to convert. Our heights in meters, we got to change that to centimeters. 1.75 meters will convert to 175 centimeters. 175 pounds, we're going to convert that to kilograms by dividing by the 2.2. Giving us 79.54 kilograms. So now, to do our body surface area in meters squared, it is the square root of our height, 175, times our weight or mass, 79.54. That is in centimeters and kilograms, so we're going to use the 3600. So second square root, 175 times 79.54 divided by 3600. We get 1.97 meters squared. Now, we just pointed out another weakness of the nomogram. Here we're going to point out a strength of the nomogram. We got a height of 175 centimeters, but let's say before we converted that, the leave our weight is 175 pounds. So we've got 175 centimeters for height. We'll put that down here, right in there, 175 centimeters. 175 pounds, so there's 170, 175 is somewhere in there. Notice the nomogram doesn't care if we mix the units together. So our body surface area, this is coming out to be right at about 2 meters squared. We came up with 1.97. So once again, it's just a few hundredths of a square meter high on the nomogram. But that is one of the strengths, is that nomogram does allow us to mix metric and standard units without having any issues. So now let's take a look at that nomogram, by the way, actually appears in your book twice. On page 192 and again on page 193 in your textbook. so that you can use that. So let's take a look at an example here. We have a patient. In this case, let's say the doctor's orders are as recommended. So you're going to have to calculate the dosage completely yourself. We have a patient who is 44 inches tall and 66 pounds. The label recommends 30 milligrams per meter squared per 8 hours. So first thing we have to do is find the BSA here in meters squared. I'm going to use the formula just because I don't mind doing the calculation. So we've got a height of 44 inches times a weight of 66 pounds. Since those are in inches and pounds, our number down here is the 3131. So square root of 44 times 66 divided by 3131.963 meters squared. So that's where we're going to start out our calculation for our dosage. 0.96 meters squared. We have 30 milligrams per meter squared, so meter squared on bottom. Per meter squared implies the 1 meter squared. 30 milligrams. Meters squared cancels out. 0.96 times 30 is 28.8 milligrams over 1, so that's just 28.8 milligrams. And then we have to put in the time for 8 hours. So 28.8 milligrams every 8 hours. Now there we left it in milligrams because we were not given the concentration in the fluid. Let's take a look at an example here where we do have to take that step. So the doctor's orders again is going to be as specified. So as recommended by on the label. So we have a patient. Our patient is going to have a height of 165 centimeters and a weight or mass of 90 kilograms. So this one I believe would be off the chart of the nomogram, and it would be just off the chart of the nomogram. So we wouldn't be able to use the nomogram here even if we wanted to. So we're first going to find that body surface area. Oops, in meters squared. So it's 165 times 90 over, since those are in centimeters and kilograms, we use 3,600 on the bottom of our fraction. So we punch it all in. The square root of 165 times 90 divided by 3,600 is 2.03 meters squared. Now let's say on our label, it specifies 25 to 30 milligrams per meter squared per 12 hours. And the fluid is concentrated at 25 milligrams in 4 milliliters. So let's take a peek at how that calculates out. We start out with our 2.03 meters squared. Put it over 1. So we need to convert. We're going to do our maximum dosage here again. So meters squared on bottom. It is 30 milligrams per 1 meter squared. So the meter squared cancels out. When I go to milliliters here now, we've got that conversion. So 25 milligrams goes on bottom, so the milligrams cancel out in 4 milliliters. So now we have this in milliliters. So let's multiply this out. 2.03 times 30 times 4 is 243.6. That is milliliters. Over 1 times 25 is 25. So divide out the 25 here, giving us 9.74. That is milliliters every 12 hours. We need to find the minimum amount there then. We're going to titrate that. 9.74 milliliters every 12 hours is the minimum, or sorry, the maximum. That was calculated on the 30 milligrams per kilogram. So let's find it for the 25 milligram, or 30 milligrams per meter squared. Let's find it on the 25 milligrams per meter squared. So 9.74, we'll multiply times 25 and divide it by 30. Gives us the low end of 8.12 milliliters every 12 hours. So 8.12 to 9.74 milliliters every 12 hours is the range of safe dosage for that patient. The next step we're going to go with these is we are going to take it to administering it as an IV using the recommendations for the body surface area. So again, the doctor is going to order as recommended on the bottle as specified. So we're going to look at a patient who is 5'2" and weighs 133 pounds. Our bottle, our label, is going to say to give 9 to 10 milligrams per meter squared per 8 hours. The label also tells us that we have 25 milligrams in 8 milliliters and a drop factor of 18 drops per milliliter. So first thing we're going to find here is our body surface area in meters squared. 5'2" has to be converted into inches. 5 times 12 is 60, plus 2 is 62 inches. So the height is 62 times the weight of 133. Since these are in inches and pounds, this is 3131 down here. So we're going to calculate the square root of 62 times 133 divided by 3131 gives us 1.62 meters squared. So that's our body surface area. So that's where we'll start our calculation over here. We put 1.62 meters squared over 1. Our dosage per meter squared, we're going to use the maximum again. Maximum of 10 milligrams per 1 meter squared. Meters squared cancel out for us. 25 milligrams and 8 milliliters. Milligrams will go on bottom, so they cancel out. 25 milligrams and 8 milliliters. So the milligrams cancel out. But then we also have a drop factor here. So let's put that in. Milliliters are going to go on bottom. It's 1 milliliter per milliliter, 18 drops per milliliter. So the milliliters cancel out, and we're going to end up with just drops here. So 1.62 times 10 is 16 point. Times 8 is 129.6. Times 18 gives us 2,332.8. That is drops. Over, on bottom, we just have 25. So we're going to have to divide out the 25. Giving us 93.31. Now that is drops. That is over an 8-hour period. So we need to convert that from 8 hours into minutes. 93.31 drops in 8 hours. We end up doing this all in one process here. I drop T on my drops. 1 hour is 60 minutes. So the hours cancel out. We've got 93.31 drops over 8 times 60 is 480 minutes. We divide that out, we're going to get an extremely small number. 93.31 divided by 480 gives us 0.194. 0.19 drops per minute. Now, what I would do with that would get rounded to 0.2 drops per minute. Remember, for IVs, we go to the nearest tenth of a drop. And 0.5 drops per minute, that ends up being 1 drop every 5 minutes. And you can set an infuser to do that. That seems like a very low number, but for most medications based on body surface area, it is a low dose. So having 1 drop every 5 minutes is not really out of line. Okay, so with that, I'm going to give you a page of homework here, a new page. Out of your book, page 196 through 197 is our body surface area calculations. We'll have you do 1 through 19 the odd. A reminder, this Friday we will review a little bit more with body surface areas and talk more about safe dosages and double checking a physician's recommended dose. Next Monday, remember, Monday, April 9th, is test 3. So we should have a little bit of time on Friday to review for that test as well. Okay, you guys have a great day, and we'll see you on Friday.